Okay, welcome back to Mr. Hassan's Maths channel. I'm now answering question number 14 from the June 2018 paper 1 from the GCE A-Level 9M80 from Edexcel. This is the UK A-Level, and this question relates to the International A-Level of Edexcel P4 paper. Okay, it's about parametric equations. So a curve C has parametric equations x equals 3 plus 2t and y equals 4 plus 2 times cosine of 2t, and t is between 0 and 2 pi, including 0, not including 2 pi. Show that all points on C satisfy y equals 6 minus x minus 3 squared. Now there are two ways that we can go about answering this question, and I'm going to show you both ways. The most kind of common way, and the way that the mark scheme would normally have as the main answer, would be to actually convert this into Cartesian form. Okay, so when they've already given you the equation, you can do two things. One of them is you can actually convert this into Cartesian form, showing that you end up with this expression. Secondly, we could substitute the values, these Cartesian form values into the parametric form values into the Cartesian equation, and show that both sides of this equation will be the same. Okay, that's an alternative way of doing it. So I'm going to start off, as this is it looks like it's not too difficult to make these, to actually form the Cartesian equation itself and show that it becomes this. So I'm going to start off by writing y equals 4 plus 2 times cosine of 2t, and I'm going to write this sine t as a subject of this equation here. So I'm going to rearrange this to make sine t the subject of this formula. So you have x equals 3 plus 2 sine t. So I'm going to take away 3 from both sides, and then I'm going to divide both sides by 2. So x minus 3 over 2 equals sine of t. So if I'm able to rewrite this cosine 2t, in terms of sine t, then I can replace it with the x minus 3 over 2, and then I will have got rid of all the t's, and I've got y and x's. So when you're writing the Cartesian form of the equation, okay, which is when it's y in terms of x, you're trying to eliminate the t's from the equation. So what I'm going to do now is I'm going to think of cosine 2t in terms of sine. Now I know the double angle formula, the cosine of 2t, can be written as 1 minus 2 times sine squared of t. That's one of the identities we should know from the double angle formula. Right, the cosine of 2t is 1 minus 2 sine squared t. So that means I can replace this with 1 minus 2 sine squared t. So I have y equals 4 plus 2 times 1 minus 2 sine squared t. Okay, so let me just simplify this a little bit first. So it's 4 plus, and you're going to have 2 minus 4 sine squared t. So that gives us y equals 6 minus 4 sine squared t. 4 plus 2 is 6 minus 4 sine squared t. So we got the 6 and the minus, and now we have to try to make this become the same as that. Now all we have to do now is replace the sine t. Now first of all, remember that what this means is 6 minus 4 times sine t squared. That's what sine squared t actually means. So I can now replace the sine t with x minus 3 over 2. So I can say y equals 6 minus 4 times, and this is going to be sine t over x minus 3 over 2. It's going to be x minus 3 over 2 squared. All right, so now when I square this, I'm not going to actually square the bracket because I want to end up with x minus 3 squared in the answer. So what I can do now is I can say y equals 6 minus 4 times x minus 3 squared over 2 squared, which is 4. They cancel out, and therefore we're left with y equals 6 minus x minus 3 all squared. And there is what we had to show. Okay, so there's the answer to part A. So we have shown that the points on C satisfy this equation by showing that the Cartesian form of the equation formed from these parametric equations is the same exact as this. Okay, so there's the answer to question number 14A. Now alternatively, Okay, alternatively, we could do this in a slightly different way. So I've just got the same question just copied over here. So what we could do here is something slightly different. We could actually start off by substituting these values into the equation given. So we could say that let's replace the y. So we have the left-hand side and we have the right-hand side. Okay, so the left-hand side is y equals 6 minus x minus 3 squared. So the left-hand side, okay, I can call this 4 plus 2 cosine of 2t. So I have to prove that they're equal to each other, basically. That's what I have to do. All right, and here you have 6 minus, and instead of x, I'm going to put 3 plus 2 sine t minus 3 squared. All right, so I'll leave this right now as it is, 2 cosine 2t. And here I'll have 6 minus, and this, the 3 cancels with the negative 3. You're left with 2 sine of t squared. All right, so now I have 4 plus 2 cosine of 2t, and here I have 6 minus 4 sine squared of t. Now, what I could do here is I can, again, use that same identity that I mentioned earlier about cosine 2t and the double angle formulae. Okay, I could use that here, and I could say cosine of 2t is equal to 1 minus 2 sine squared t. So I can replace that with that. So 4 plus 2 times 1 minus 2 sine squared t. And now this is 4 plus 2 minus 4 sine squared t, which gives me 6 minus 4 sine squared t, which is the same as this. Okay, so we can now say, for example, left hand side is equal to right hand side. Okay, therefore we can say that this is true, that basically it satisfies the equation. Therefore y does equal 6 minus x minus 3 squared. Okay, we can say that all points on C satisfy. Okay, we can say therefore all points on C satisfy this equation. All right, so that's something that we have to, if we do it the second way here, okay, where we're using the answer given, we have to write a little statement at the end that, the left-hand side is equal to the right-hand side. Okay, so therefore proven, something like that. Okay, so therefore it's proven. We have to write a little statement at the end. If we just do the first way where we actually form the Cartesian equation of the curve, then that's fine. But if we use what's already given, we have to make a little statement saying that, show that they're the same, the left-hand side and the right-hand side are the same, therefore that proves that all points on C satisfy this equation. Okay, so there's the answer to part A, 2 alternative ways of answering it. Now for part B. Now, part B, there's a space on top here which I've left, that's for the sketch, but it says here, part B, part 1, sketch the curve C, and then it says, explain briefly why C does not include all the points of y equals 6 minus x minus 3 squared. So for part 2, it's kind of like giving you a clue as to how we should sketch it, okay, in case we just go and sketch it. Because if I was to sketch 6 minus x minus 3 all squared, and, just take x as all real numbers, and not consider the limitations, because this is formed from our equation. Okay, this is formed from our equation. Okay, our parametric equation. Yeah, so the curve C, remember, the curve C is defined by this first. Okay, it's defined by these. This is what defines the curve C, and this is just the Cartesian form of it. So if there's any restrictions on this, those restrictions will be applied to this also. So if I was to just plot this, I see that we have a quadratic. So it's going to be a minus x squared. There's a minus in front of this bracket, so it will be minus x squared. So we're going to have a frowny face. And we can see that when x equals 0, if I put x as 0, I'll have 6 minus 9, which is negative 3. So y equals negative 3. So it's going to go through somewhere down here. And we can see that when y equals 0, you'll have 6 minus x minus 3 squared equals 0. So you'll have 6 equals x minus 3 squared. So x minus 3 is equal to plus or minus the square root of 6. So x equals 3 plus or minus the square root of 6. So you're going to have 3 plus square root of 6 somewhere over here, and somewhere over there. So it's going to go like this basically. It's going to turn and come down again. That place would be 3 minus root 6, and that would be 3 plus root 6. And the vertex of this is going to be the value of x that caused this bracket to be 0, which is 3, sorry, and whatever's left behind, which is that plus 6 for the y. So that would be 3, 6. That would be the vertex at the top there. All right, so that's how it would look if it was completely unrestricted in terms of there was no conditions applied. It was just this curve. It was just this curve without knowing that the curve is originated from this Cartesian form, then that would be how we draw it. We continue going on and on both ways. However, there is some restriction, okay? The domain and the range of this is defined by what the original parametric equations were that formed this, and that's something that's really important, which is, there's not really that many questions that ask that, test us on this actually understanding. So I was quite happy to see this question because it's possible that they can ask us this, right? So if they ask you this as a surprise and you've never seen anything like this before, then that will be a problem. So hopefully this will help in case they do ask such a question, right? So in this particular paper, they did give us some indication, and they gave us a clue that why we can't include all the points of this curve as we would, okay, if it was not formed from this parametric form. So what we should understand is that the x part of the parametric equation, that is basically the domain of this is the domain of the Cartesian equation. And the y part of this parametric equation is the range of the Cartesian equation. Right, so if you want to find what the domain of our Cartesian equation is, we have to see what is the range, what can be the output of this. What values can 3 plus 2 sine t take in the restricted t values that they gave us? So if we think about 3 plus 2 sine t and think about the biggest and smallest values of x. So if we think about the biggest value that x can be, all right, we can say x max, it's going to be when sine t is equal to 1. So x max is when sine t is equal to 1, so that's going to be 5. 3 plus 2, which is 5. And we can say x minimum is going to be when sine t is equal to minus 1. Because the maximum this can be is 1, and the minimum that this can be is minus 1. Okay, the value of sine t, especially in this range here, right? So we can see x minimum is going to be 3 minus 2, which is 1. Okay, so 3 plus 2 and 3 minus 2. So we can say the domain of our function is going to be between 1 and 5. X values between 1 and 5. That's the domain of our Cartesian equation. Okay, so that's the domain. And for the range, we'll look at the y values. So we have y is 4 plus 2 cosine 2t. So again, the maximum value that this can take is when this is equal to 1. And this will reach 1 in this range. So it's going to be y max is going to be 4 plus 2, which is 6. And y minimum is going to be when this is minus 1, which is 4 minus 2. Because this is going to be minus 1, so 4 minus 2, which is going to be 2. So the range of our function is between 2 and 4 plus 2, which is 6. Okay, 2 and 6. So the y values range between 2 and 6. Okay, so that's the domain and range of our function. So basically, we want to sketch the graph of y equals 6 minus x minus 3 squared, and the domain, as we mentioned, is between 1 and 5. 1 and 5. And the range is between 2 and 6. Okay, so that's what we have to sketch here. So let's sketch it in this space over here. I'll make my pair of axes. there we have x, here we have y. Okay, so we can see that the vertex, as we mentioned before, is going to be x equals 3 and y equals 6. Whatever value of x makes this 0. So it's going to be 3, 6 is the vertex. It's going to have this. So I'm going to first sketch it like as if it was unrestricted, and I'll get rid of the parts that we don't need. So just to make it look a bit neat. Okay, so now we know that this is 6 and this is 3. All right, now let's have a look. The domain is between 1 and 5. Okay, so when x is 1, okay, when x is 1, you're going to have hopefully this will be 2, right? So when x is 1, you're going to have 6 minus, and you have 1 minus 3, which is minus 2 squared, which is 6 minus 4, which is 2. That's correct. So that's going to be 1, 2. Right, so that's where it's going to start at 1, 2. So we can get rid of everything before this. It doesn't exist over here. It starts from 1, 2. Okay, and where it ends is the domain is 6. The domain is 5. Okay, and so when x is 5, you're going to have 6 minus 5 minus 3 squared. So it's again going to be 6 minus 4, which is 2. So it's going to again be at 2. At that same level over there. So it's kind of symmetrical, of course, because it's this quadratic type. So therefore, we have our sketch. Okay, the domain is limited to this section over here. Okay, the domain is limited between 1 and 5, and the range is limited between 2 and 6. Okay, so that's how we can draw our function according to the limitations in its domain and range. So the thing that many people do not appreciate in such questions is that the domain of the Cartesian, the domain of the parametric equation is basically the x part of it, and the range is the y part of it. Okay, so here it's quite easy to work out the domain and range. We could have sketched the graphs as well if we wanted to. Okay, we could have sketched them, but for these, for example, 3 plus sine 2t, between 0 and 2 pi, okay, it doesn't change horizontally, but it changes vertically. First thing is the values are multiplied by 2, and then you add 3 to them, so it's going to start from 3, and the highest point would have been 1, so 2 times 1 is 2, plus 3 is 5, so it's going to go up, and the lowest it's going to go down is 1. It's going to go like this, something like that, okay? That's a sine curve between those values, and we can see the biggest value it gets to is 5, and the lowest value it gets to is 1. And for the other curve, if we this is plotting basically x against t. Okay, x against t. And to find the range, we're going to plot y against t. So this is y against t. Okay, that will tell us the range of this function. Okay, and we can see y is 4 plus 2 cosine 2t. So the cosine curve between 0 and 2 pi, it would normally go once, but now it's going to go twice. So it's going to follow this pattern. All right, it would go like this. And then it will just repeat the same shape again. Not very well drawn, but anyway, that's cosine 2t. But this has been multiplied by 2 and then 4 added to it. So this, which would have been 1, is now going to become 2, and then 4 is added to it, so it's going to go up to 6. So the whole thing will raise up to you'll add 4 to it, so it'll raise up to 6. So this minus 2 is going to go up to, if you raise it up 6 places, okay, this would have been minus 2, okay, and minus 2 plus 6 is going to give us, for the y, it's going to give us 2. Sorry, minus 2 plus 4 is going to give us 2. Minus 2 plus 4 is going to give us 2, so you're going to end up with 2 here and 6 on the top. Right, so you can see how that, this would be the range of our function. Okay, so the domain is when you plot basically x against t, and the range when you plot y against t. In this case, we don't really have to plot them because we can see from the sine and cosine curve how they're going to look in terms of that range. All right, the maximum and minimum values you can tell by just putting sine t as +1 and -1, cosine 2t as +1 and -1, and you get those maximum and minimum values. So there we have the answer to part 1, and part 2 is asking us to explain why. Okay, there are some restricted values explain briefly why C does not include all the points. Okay, we can say because C is based on the parametric equations for which, we can just put for which X is the domain and Y is the range, and there is a restriction. There are restrictions. There are restrictions, something like that. Okay, there are restrictions in the domain and range given by this limit for 0 to 2 pi for t. Okay, now for part C. We're told that the line with equation x plus y equals k, where k is a constant, intersects C at two distinct points. Okay, state the range of values of k, writing your answer in set notation. Okay, so x plus y equals k is a straight line. Okay, so if we rearrange that, you have y equals minus x plus k. So you got y equals mx plus c, so the gradient is -1, and c is the place where it hits the y-axis. Okay, so now, if the gradient is -1, it's going to look something like this. Okay, it will look something like this. Let me just make it a bit thinner. It will have this type of shape like this, right? So it's going to look something like that. So we've got to find the range of values for which this is going to have two solutions. Okay, so we can see that's the range of values of k for which there will be two solutions to this. So basically where this intersects 2 times. Okay, so you can see that there's going to be a limit over here, okay, where this line passes through this point, which is 5, 2. That's one place. If you go any lower than that, there's only going to be one intersection. Remember, this function only starts from here and ends there. So there's only one intersection in all this area here, and there's no intersection here. So we want the value of k, which is the y-intercept, such that the line passes through the point 5, 2. Okay, so that will give us one of the limits, and the other limit will be when basically this is a tangent to the curve. When this line is a tangent to the curve, that's where the other limit's going to be. You can see that's where there will be the limit. Just before that, it's a tangent, there's two solutions. So the region, the places where there's going to be two solutions is when k is this value here. You can call that k1. And when k is, remember k is the y-intercept, and when k is just below this value here. Okay, so it's going to be like between those two values, including that value, but not including that value. So we need to find what those values of k are. Okay, we need to find what those values of k are. All right, so for the first one, we can work it out by using the fact that this line, which is y equals minus x plus k, passes through the point 5, 2. So we can even use in this form, we can say x plus y equals k. It must pass through 5, 2 for that's like the lower limit of k, k1. Passes through 5, 2 for k1. Okay, so we can say that this is the x and this is the y value, so therefore we can say k1 is equal to 5 plus 2, which is 7. So that's the lower limit of the line. Okay, the upper limit of k is going to be up here, where the line is a tangent to the curve. Okay, so we can say that the upper limit is going to be when the line, when x plus y equals k, is a tangent to C. Okay, now how do we know when it's a tangent to C? When we try to basically solve these equations simultaneously, we find that there's only one solution. Okay, so when x plus y equals k, solved simultaneously with y equals 6 minus x minus 3 squared. Okay, so we can say is upper limit is when x plus y equals k is almost a tangent to C. You can say almost a tangent, because when it's a tangent, there's only one solution. So it's just before it reaches being a tangent. So what we can do here is we can say, let's find out when there are two solutions. Okay, the values of k for which there are two solutions, that will tell us that limit. Okay, so that's when b squared minus 4. So first of all, we have to basically solve these simultaneously. So I'm going to rewrite this as y equals k minus x. And then I'm going to solve these two simultaneously by replacing the y here by k minus x. So k minus x equals 6 minus x minus 3 squared. Now if I solve this equation, it will be in terms of k here. So I have k minus x equals 6. Now if I expand this bracket, I'll have x squared minus 6x plus 9 inside that bracket. So k minus x equals 6 minus x squared plus 6x minus 9. Now what we can do is we can simplify this. We have k minus x equals, you have minus x squared plus 6x, and 6 minus 9 is minus 3. So bringing everything on one side, you have x squared minus 6x minus x plus 3 plus k. So this gives us x squared equals 0, So x squared minus 7x plus k plus 3 equals 0. So now we want to know when there are exactly two solutions, okay, and we can see that that will be when b squared minus 4ac is greater than 0. Okay, so that's going to be a is negative 7, b is 1, sorry, what am I talking about? A is 1, b is negative 7. A is the quotient of x squared, so a is going to be 1. B is the quotient of x, so it's negative 7. And c is the constant, which is k plus 3. So we have b squared minus 4ac is greater than 0. So b is minus 7, so you have minus 7 squared minus 4 times 1 times k plus 3 has to be greater than 0. So you have 49 minus 4k and minus 4 times plus 3, which is minus 12, is greater than 0. So we end up with 37 minus 4k is greater than 0. So minus 4k is greater than negative 37. Divide both sides by negative 4. The sign must change direction. So k is less than 37 over 4. So therefore we know from the first condition that k has to be less than 7. So k must be, this k1 is 7, and this k2, which is where it's a tangent to the curve, where that's a maximum it can be, is 37 over 4. So this is 37 over 4, and this is 7. So we can see that it lies between these two. So I could have answered this by making it equal to 0 and finding out where it's exactly equal to being a tangent, and then it'll be less than that. Or I could have worked out this is the limit for it to be have two solutions, which is just before it becomes 37 over 4, just before it reaches there. It's just when it's below this, which is what we're going to see from here. So basically the values of k are between 7 and 37 over 4, including 7, but not including 37 over 4. Okay, so we can say k is such that, they said in set notation, so k is such that k is between 7, including 7, but less than 37 over 4. We can write it like this. If we want to, we could say, or k is such that k is greater than or equal to 7. Okay. Intersection with k is such that k is less than 37 over 4. Okay, we could write it both ways. I think this way is nicer personally. And there we have the answer for this question, which is a long question, question number 14. A lot of things involved in this question, which are very important, especially this domain and range business for these parametric curves. And that's something which does not come up very often. If you do see another question from these past papers, whether it be C4, C34, some of the British Edexcel papers, then please do let me know, because it is possible that such a question does come up and you should be ready for it. Thank you for watching and see you soon.